sort of better.
Check.
Oh, hold on. Thanks, sorry.
All right, everybody, back to your seats. You're not going to want to miss this. All right, cool. Everybody back? Excellent. All right, so our next speaker is Elaine Stewart. We've been friends for a while now. She was also one of the scientists that's featured in the VR space, so definitely check that out after her talk. So I'm going to pass it off to her, and then we'll do some Q&A with both Elaine and Paul after, so hold your questions until then. I'd like to introduce Elaine Stewart.
Thank you so much, Ashley. So I will be speaking actually a bit about my specialty for the Webb Telescope, which is contamination engineering. Some people may have heard the term before, some people might not be familiar, but the whole goal behind being a contamination engineer is actually keeping the sensitive surfaces, especially our beautiful optics, as clean as possible so we get the best images possible. And I wanted to just point out, I'll be speaking a bit about how we accomplish this throughout the entire duration of the mission. But I was thrilled to be able to go to the launch campaign that we had in French Guiana. So this is a picture of me with the Ariane 5 rocket. Just a little bit of comparison for me compared to how large the rocket is. Okay, so with our 4 main science goals, we're looking at some of the first light that was created after the Big Bang, how are galaxies formed, what is the star life cycle like, the birth and the death of stars, and additionally, planetary systems and origins of life. So you can see along the bottom, with each various telescope, we have different regions that they are specifically designed to. And for Webb, we're looking in that infrared wavelength so that we can look back at some of these really distant and really faint targets of observation. Now, what's really great is that we can use in combination these observatories together. So we were just looking at some images from Paul where we were comparing and even overlaying sometimes images from Hubble and Webb together. And to see some of these first objects, we must have the optics be very large. Now, if we're looking just with our human eye, it's relatively small and we can only collect just a small fraction of starlight. But for these very, very distant objects, we need to make sure that we have a primary mirror that is wide enough, large enough, so that we will actually be able to gather all of these light particles, which are photons. So we have these telescopes that are much wider than our eyes, so we can collect more starlights and then make those really dim objects appear brighter. And after we looked at, what are our main targets of observation, we came up with that the mirror had to actually be 6.5 meters, which this is difficult from a contamination engineering perspective because we actually have an open architecture. So the optics are unprotected throughout the integration and testing phases of the Webb mission. Additionally, we had to actually fold the telescopes that we could fit into the Ariane 5 rocket. So here's a quote that was from 2010, Alan Dressler, who's an astronomer. NASA had a strong desire to build the first of the new telescopes rather than the last of the old. So I wanted to highlight here all of the creative engineering that went into the Webb telescope will be implemented in our future projects too. And in each various engineering discipline, we had to come up with new methods to actually implement and be successful with the Webb telescope. So again, to see that very faint signal, we had to be very, very clean. So we had a new set of challenges for contamination control, or CC. So for the first of the new telescopes to be clean, we would have to have new contamination control approaches. So these exposed instruments and optical surfaces need to be kept clean over the years that did turn into decades, which encompassed building, testing, transporting, and then actually launching the observatory. We actually had to do all of this work in many different facilities in the US and around the world. So here's a depiction showing that we started at Goddard Spaceflight Center in Greenbelt, Maryland. We then performed our environmental testing, which also included having protection, which involved a tent to kind of create a barrier between leaving the clean room and trying to keep the observatory in the best conditions possible during testing, to our STARS transporter, which you can see in this third image on the top, that is actually like a mini transportable clean room, which then took us to Johnson and the testing in the cryogenic vacuum chamber, make sure that we would actually be able to operate everything while we were in space. Then over to Northrop Grumman in Los Angeles, California, for the integration with the sun shield to become that full observatory. And then back into our STARS transporter when we went to French Guiana and the launch site for those final steps before launching to L2. Now at each phase we had contamination requirements in both particulate and molecular that we were tracking. So this was actually created as a collaboration with the science team, where we balanced the contamination levels versus stray light and sensitivity. So for particulate contamination, particles can create scatter, and this will actually impact the observations. So if you think about it, if you have a, like even think about a dirty window, if you look through that, you can't see as much if there's dirt on it, particles on it, and it's kind of the same way with our optics. So if we have particulate on it, then we will be able to see less, and it will actually take us longer when we are trying to make our observations. So we want to make sure that we don't lead to longer observation times and cut down the science. We want to have the cleanest optics possible. So we actually determined our end-of-life requirements would be 1.5% area coverage. So that's just a metric that we're able to analyze and track throughout the process so that we know, how much of the surface is covered with particles and what size particles are actually there for our primary mirror. And then for the secondary mirror, which is much smaller, we had 0.5% area coverage as a requirement. Now, this secondary mirror requirement is a bit more stringent because, as I mentioned, the mirror is smaller, and that is the second optic that is reflected into the instrument. So we want to make sure that it is as clean as possible for the best science to be accomplished by the instruments. And this data down at the bottom is actually the analysis that was performed in conjunction with the scientists, looking at the stray light so that we could figure out the cleanliness level that we needed to achieve, and also the transmission budget. So if you have different levels of particulate or molecular contamination, how will that actually affect what you're able to see? Now, to keep in line with our particulate contamination requirements, we actually cleaned the mirrors. So right after we went into the cryovacuum chamber testing at Johnson Space Center, we had developed and tested on a surrogate at Goddard the best way to clean the mirrors, and we actually took around 2 weeks to perform this very stringent, very careful process of cleaning every single mirror on the primary mirrors and the secondary mirror too. Now, we actually did perform this a second time prior to going to the launch campaign, but this is one of our ways to reset the optics throughout the integration and testing. So let me talk a little bit about molecular. Molecular contamination is anything that can be like a thin film or a grease, and it's non-volatile residue, or NVR. We can have carbon, which can polymerize post-launch, and then even water. So water can be released once you get to space, and this water will quickly freeze. We were just talking about how cold the telescope has to operate, and that can actually ice up your optics or even some of your deployable mechanisms. So we need to be very careful about our molecular contaminants. So we determined that for the primary mirror, it would be 392 angstroms. This is accounting for various measurements in the NVR, carbon, and water ice. And then for the secondary mirror, it was 330 angstroms. So throughout the integration and testing process, including our chamber testing, we found that our biggest threat to contamination and meeting these requirements was actually monitoring and preventing against water and ice. So we actually implemented specific SLI, which is single layer insulation. We use it a lot for thermal controls, and we can actually orient it in ways to help protect our optics and our sensitive surfaces. I'll talk about that a bit more later. We also worked closely with the thermal team to examine the cool down profiles and the warm-up constraints. So this was during our cryo vacuum chamber testing, but we implemented all of the lessons that we learned on it for on orbit. So to protect our sensitive surfaces, we want to make sure that anything that we care about is going to be warmer, so the contamination will gravitate towards cooler surfaces. So this involved lots of complex modeling and analysis to make sure that we understood the cool down profile on orbit, and we would actually be able to ensure that we weren't going to trap contaminants on any of our sensitive surfaces. So let me talk a little bit about a project that I have the pleasure of working very closely on, and this was actually how we obtained some molecular transport data and mitigated against water and ice for the Webb telescope. So here we have the primary mirror, and then this is the secondary mirror. This is the inboard hinge. So as you can see, while the secondary mirror is stowed, which it was for about 10 days after the launch, the inboard hinge is very, very close to the secondary mirror. Now, during these 10 days, the telescope is cooling down to operational temperature. And in that time period, we're concerned about water being released and ice accumulating. And in this inboard hinge, we actually have, what we would consider outgassers. So outgassing is basically the release from a material in a, like if you think of like a new car smell. So it's kind of like that. We monitor every single material that we use on the telescope. We test everything to make sure that we don't have any high outgassers that could actually result in molecular accumulation. But here in the inboard hinge, we have what we would consider some high outgassers. So there's some cables, some motors, we have a radiator that has a coating on it. So we needed to find a solution for how could we mitigate against possible ice accumulation on the secondary mirror in this configuration. This is actually a view of what it looks like without any of the thermal enclosure, any of that SLI that I talked about. So what we did is we actually performed inspections and we performed some modeling to figure out how we could improve the geometry of the thermal enclosures and actually provide directional venting away from our sensitive surfaces. So we took off all of the blanketing that was originally there since we had found some gaps, and we made sure that we had preferential venting away from our optical surfaces. And here you can see just a reflection in the secondary mirror, just how close this inboard hinge was. I just also wanted to mention that this was really important to us because we didn't have a heater on the secondary mirror. So if ice did accumulate, then we would not have a way to actually be able to warm that up and get the ice off. So we solved this portion of the problem by actually making sure that there was specific adhesive contact of all of the thermal SLI. We made sure that there was no line of sight for any of the high outgassers, so any of the cables or the radiator. We tried to vent away from the optical surfaces. And at the same time, we actually performed some testing. So we used the cool down profile. Now this was a model that was given to us by the thermal team in conjunction with the scientists, so that we could understand exactly when the heater was going to be turned on for the inboard hinge. Now, don't have a heater on the secondary mirror, but we do have a heater on the inboard hinge, which is really where that release of water can happen. So at the time the inboard hinge was turned on, the secondary mirror was cold enough to condense water. So we needed to make sure that we again made those modifications to the thermal enclosure. And then we performed testing to make sure that we understood what kind of outgassing rates we would expect to see from the inboard hinge hardware. And the result of this was actually that the Webb on-orbit commissioning team performed a bakeout of the inboard hinge prior to the secondary mirror deployment, but while the optics were still too warm to actually condense any of the water. So this made sure that we would not have any ice accumulation on the secondary mirror that we'd have to worry about for the rest of the operations of Webb. Now, I've spoken a bit about the mirror cleaning, which was direct contact with our flight hardware, and also the inboard hinge modifications protecting the secondary mirror, also direct contact with the flight hardware. But another important aspect of contamination engineering is making sure that any facility the flight hardware goes into, any ground support equipment that comes into contact with the flight hardware is also at the same requirements. So I'll tell you a little bit about the Ariane 5 fairing. Now this is a depiction, well it's a picture actually of the Ariane 5, but the fairing is the very top portion here. That's where the Webb telescope sits in. So again, we inspected, monitored, cleaned, not only the observatory, but anything that came into contact with the telescope. So here's a graphic just showing you where Kourou, French Guiana is. Our launch campaign took place last fall of 2021, and we actually had to move between a couple of different facilities for our final integration, the fueling, and then going on top of our launch vehicle. This is just a little bit of information about what we had to do in each facility, not only at the launch campaign, but every facility that the Webb telescope was in throughout the duration of the mission. So usually as contamination engineers, we go in, we try to understand the airflow in each clean room. We work to do inspections, so we're usually using white light and ultraviolet light so that we can understand if there are any particle generating areas, things that we need to clean up. And this was something that we did in, this is the bath encapsulation hall at the launch site. So this picture shows you just how large this room is, because we have the Ariane 5 fairing. This was our fairing for the mission. The Ariane 6 fairing, which is for the next rockets to come. We were one of the last Ariane 5 missions. Our Webb telescope over here. And then actually another measure that we implemented with contamination in mind, which include our HEPA filters. So HEPA means high efficiency particle air filters, and we actually had these just so that we could control the microenvironment around the Webb telescope. And we performed what's called computational fluid dynamic models to understand how the particles would flow around the telescope, making sure that we weren't going to cause more problems by our airflow than help. So we wanted to make sure that we weren't going to be pushing particles onto any of those sensitive surfaces. And an important part in understanding whether we need to implement HEPA filters or not is taking particle counts. So this is a picture of me in another facility at the launch site measuring our particle counts. Now, when we're talking about particle counts, they're actually quite small. So we were operating in class 10,000 clean room, which is mostly based on 0.5 micron size particles. Really, really small. So this particle counter is going to tell me in a cubic foot of air how many different particles I have in various bin sizes. So the 0.5 range, 1 micron particle range, and I'm also able to get this data from some samples that we have placed around the facility too. So all of this work happened in the facility to make sure that we were ready to receive the telescope and receive the fairing. When we actually received the fairing, we performed a final cleaning. There were initial cleanings that were actually performed at Beyond Gravity in Switzerland, where the fairing was from. So this final cleaning actually involved Beyond Gravity representatives, ESA, NASA, and CNES from the launch campaign. Here you can see the Ariane 5 fairing, and this is scaffolding next to it. So the Ariane 5 was actually placed on top of the scaffolding so that we could walk up inside of it and perform white light and UV inspections to make sure that it was as clean as possible. Now, we wanted to do this because this was the last environment that Webb was exposed to before launching. We had been so careful throughout the entire campaign to make sure that it was as clean as possible. We wanted to have the fairing be just as spectacular as all of the other environments it's been exposed to. One of the contributors that we were most concerned about is the fairing acoustic panels. Now, in this view, you can actually see that there are quite a lot of them. So these panels were actually tested at Goddard Spaceflight Center and at the ESA ESTEC facility in the Netherlands, so that we could understand what kind of particulate fallout to expect from these panels. They did make modifications for Webb so that we would have the best possible environment. And here's a picture of me actually inside of the fairing inspecting. You can't tell from the angle of the picture, but I think it was somewhere way up here at that point inside of the fairing. And after we cleaned the fairing, we wanted to make sure that those final days, right before encapsulation and during encapsulation, Webb was seeing the best environment possible. So the Kness team actually built what we have called the air shower curtain, which is depicted here. And this area that you're seeing is right here. So it's kind of a nightmare that this door opens to the outside. The tropics in French Guiana involve many, many challenges, but we were able to contain the environment, kind of create a microclimate where we could work for the last couple of days while Webb was on the launcher, and then have a safe encapsulation of the Ariane 5 fairing on top of Webb. So through all the different mitigation efforts that I've talked about, looking at the particulate accumulation, molecular accumulation for both the flight hardware, our facilities, and any kind of launch vehicle or ground support equipment that come into contact with it, we were very successful in our efforts. This quote mentions that they found no critical issues or no measurable contamination that is actually blocking our optical path for Webb. So we're able to successfully gather the light from distant galaxies and deliver it to the instruments without issues. I just wanted to show you some numbers that we're really proud of. I mentioned the end-of-life requirements for the primary and the secondary mirror. So first we'll look at the particulate. The primary was 1.5, and we measured 0.754. For the secondary mirror, our end-of-life requirement was 0.5, and we had measured 0.149. And for the molecular, you can see we measured 45 angstroms, where that end-of-life requirement was around 300, which means that we came in way under our requirements, and that just helps the scientists to make these observations in shorter amount of time so that we can do more science with the mission. Okay, and with that, I'm just so thrilled to have been here, and thank you so much for having me.
Thank you, Elaine. So now we're going to open it up to the audience so you can ask questions to both Paul and Elaine about anything you saw here tonight. I'm sure you have a ton of them. So I'm going to pass this one around to the audience.
That's fine.
Okay. Oh, you have one for the audience. Okay, cool.
Thank you.
All right. Yeah.
So I'm really curious about the collaboration of ARC with this Webb telescope. How did you connect with them and then make the ARC?
I wasn't expecting this one. So how did I connect with the Webb team in general? Or yeah, okay. So yeah, it's been 7 years now, but I did this great program called New Inc., and that's the New Museum's Art Tech Incubator, and a great sponsor of our exhibition. So thank you, New Inc. But while I was there, one of my advisors, Kathleen Ford, was on the board for the Artist in Residence program at SETI. So I went out to Hat Creek Radio Observatory and hung out with all the SETI people, and they had a party the one weekend and brought a bunch of NASA Ames people there, and I laid out in a telescope field with a bunch of NASA scientists, and they invited me to see NASA Ames and do a tour of NASA Ames and see what science they were doing there. Then they passed me out. They were like, you should see a rocket launch. So I went to Kennedy and saw the launch of the OSIRIS-REx mission. And while I was there, they're like, have you heard of this cool new telescope they're building up at Goddard, the James Webb Space Telescope? And so that was my next stop. I went and I met everybody on the Webb team, and I saw the telescope while it was on Earth in the clean room, and that's history. I stayed there, and I was like, this is what I'm going to focus my artwork on. I was just so taken by the mission and by the science they were going to do. So yeah, hung out there. And then I met these cool guys, and you know, they told me all of the cool stuff they were doing, and I was just so inspired. So how could you not be? That was a great presentation.
Yeah.
This one's yours, right? Yeah. Cool.
Here it is.
I have a slightly uncomfortable, potentially controversial question.
Go for it.
I'm not scientific in background, so I'm curious, as you guys have worked with NASA, have you felt yourself become more or less religious, or as with things you're seeing?
Okay, I will go first. I think that it has given me an interesting perspective in terms of, you know, we were talking just earlier before we began the presentations about what will we learn with Webb, and the Hubble deep field image where they pointed to part of the sky where they didn't know anything about it, just to see what can we learn when we look here, and they found, you know, like hundreds of thousands of galaxies. Now we're talking about how we can't even find a dark spot in the sky because Webb is so powerful. So I think it really gives a perspective as just to how probably insignificant we are. And we don't know what's out there, but we keep asking the questions. You know, we have what are called decadal surveys, where every 10 years we look at what are the next big questions that we want to find out and what we want to solve. And I think that what's really great is we have these international collaborations where it doesn't matter, you know, what your background is, what your religion is, but we want to work together. And I think that there's no way that we're going to be able to find out more about perhaps where we came from if we don't do that. So I think that it makes me feel insignificant but excited, because there's so much that we are still wondering about and questions we haven't even asked yet that hopefully we'll find out more on.
Yeah, well said. You know, Ashley said something earlier when we were talking before this, and that I thought was really great. It's that like science, religion, art are all asking kind of the same questions but from different angles. And I'm not a religious person personally, but like Elaine has said, you know, humans tend to get really hubristic, right? Hubris is a problem with the human race, and everybody thinks they know everything. And the cool thing about this work is, you know, it's humbling. You realize how really amazing everything is, and you think you have everything figured out, and then we build a new tool like this, and it's, you know, puts us back in our place. So, you know, the more we learn about nature, the world around us, the more wondrous it becomes, at least to me. And I think that's maybe its own spirituality, but that's me.
More questions? Anybody else? Oh, Nat Timms. That's a great question for us.
No, I don't. I mean, you don't know what it is. Well, okay, I got two questions. First off, I'm repressed to say I don't know what an angstrom is, but you didn't give, so it was a bit hard to follow, but I did have a major question about, you said that there were, inside the fairing, there were like audio, not audio panels, but panels that block sound.
Mm-hmm.
Why would you have that?
Right, so the launch environment, especially the first moments of liftoff, the sound, the intense sound it's crazy intense. Broad spectrum, it's, like I said, it's louder than way louder than being at the front row at a Led Zeppelin concert right in front of Marshall amps. It's literally enough to scramble your insides and kill you. So the sound, there's this acoustic environment. Most of it lasts only the first like 7-10 seconds of a launch, but it's really bad. So you know how like in anechoic chambers or sound studios they'll have the foam cones on the wall and stuff like that? it's all to help absorb sound, and these acoustic tiles are basically that. They help attenuate the sound from the outside, which a lot of it is just reflected from the rocket exhaust off the pad and the structures, and getting it attenuates it before it gets to the insides and reaches the observatory. And acoustic energy, sound is a wave like light. It's a different kind of wave, but sound is short waves, right? And like mechanical vibration, those are really long waves. So acoustic stuff, the short wave couples with something comparable in size. So small things, electronics, little stuff, really lightweight things get coupled into that acoustic energy really well, and you want to attenuate that before it gets to the satellite. So that's what those tiles are all about. Sorry for the long answer, but
Yeah.
they because of their nature, like to absorb sound, the way some of them are made, they tend to like want to shed particles like a suspended ceiling tile will when you have an earthquake. So hence, all the work
Particulate.
she
Yes,
did
yeah.
on keeping that from particulating.
Right.
Oh, okay.
Just a quick question. After the launch, we heard a little bit about micro meteors and
Yes.
the damage that was caused.
Yes.
How did you design against that, knowing that it could happen? What
So,
was-
yeah, no, that's a great question. So we knew we would get the occasional micrometeoroid hit, and by nature of this design, we had to build this thing with this mirror that's just unprotected for the most part, so that it could get cold by just radiating its own heat to deep space. So we knew we had a kind of an Achilles heel in this design, but it was by necessity. But we understand what the micrometeoroid environment is out in the L2 region. We have folks that work at the Marshall Space Flight Center that have studied for years, and they understand, they've measured, and they've modeled. We have good understanding of what the micrometeoroid environment's like. And so about once a month we get a really tiny hit, and we're talking small stuff. I mean, like particles of dust you couldn't even see, but they're whizzing at like 10 or 20 kilometers a second, so they can do damage when they hit something. But those things are almost imperceptible. But we did have one big hit in late May that got everybody's attention, and then I ended up having to say something in the New York Times about it.
It's always bad if you end up in the New York Times.
Yeah. And so we knew that could happen, but we thought those are like 1 in 2 year, 1 in 5 year events or something. But we long answer, I'm sorry, but when we designed this thing, we said this thing's gonna get hit occasionally. We need to design some margin into it, and we need to make it resilient. And so we ended up building a beautiful mirror, and it's actually much better than what the scientists require to do their science. And so it can degrade. We actually have a budget for this thing getting distorted slowly over time because micrometeoroids hit it. And we're kind of right in line with the expectations there. The thing that hit in May was like, crap, is that a 1 every 6 month thing? Because that happened only 6 months after we launched, or is it really one of these 1 every 2 or 5 year things? And we just, small number statistics, it's kind of hard to extrapolate from one event, right? So, yeah, but it played, the press ate it up, and the general public's like, oh, cool, this thing's getting whacked by bees.
Wham!
Is it gonna break? Is this messed up? What's going on? So, a lot of drama, but it's not that, bottom line, it's not that big a deal. We budgeted for it, we knew it would happen, and it's kind of as we expected.
And that one also hit in an area that was already kind of blocked
Yeah.
by the
By the
optical
secondary
structure, by the
support
struts.
structure.
So that was
And
convenient too.
We've done some understanding this thing when you can't go out and touch it and look at it is like Braille on steroids, because so all the telemetry we get back from this thing, and because we can actually take pictures of the primary mirror as part of tuning it up every few weeks, it's really, this thing we ended up designing by accident a really sensitive micrometeoroid detector. And we got unlucky with that one particle in the sense that there's some structure behind each segment that is part of the whole system that allows us to move each segment in any direction, right? Up, down, sideways, rotate it, and tilt it. And we can even change the shape of each mirror segment just a little bit so that they all match. And if you put a little micrometeoroid, basically they go right through the face sheet of these mirrors, which are only 2 millimeters thick. The mirrors are like this thick, but most of the material's hogged out, machined away. And so the face sheets are really thin. And they're made of beryllium, by the way, which is really stiff, lightweight material. So it ended up hitting one of these structures behind the segment that's used to position the mirror. And so that warped that substructure, and that introduced some extra distortion into that one segment. But the cool thing is we got 18 segments. We built them really nice. That one segment's more distorted than the rest now. But when you average it out over the whole system, it hardly made a difference. So just to put in the numbers, since light is a wave, you can build a perfect optical system, but you'll never get better than the diffraction nature of light itself. So when you build a telescope, the surfaces can be perfect, they can be aligned perfectly, and you'll still be limited by fuzziness. Just that's a natural result of the fact that the way the light diffracts, and that's called diffraction limited system. To be diffraction limited, the sum of all your errors, slight surface imperfection, alignment errors, whatever, you sum them all up, they have to be less than 1/14 the wavelength of the light you're looking at to be diffraction limited. So we're diffraction limited at 1 micron. We were designed to be diffraction limited at 2 microns. So we're way better than necessary. And so if I divide 2 microns by 14, I get roughly 150 nanometers. A micron is a millionth of a meter. A nanometer is a billionth of a meter. So 0.15 microns is the total error we can have in this whole system, soup to nuts. This mirror, that mirror, the other mirrors, all the instrument stuff. And the amount allocated to this mirror was, we're like half of the budget allocated to the main mirror. Even after that, that one bad micrometeoroid hit, we only had it amounted to a handful of % change. So really, I'm really good at giving long answers. I apologize. But
Thank you.
People want to know.
But we freaked out a little bit in May. We're like, oh crap, I hope this isn't more frequent than we thought. Are our models right? So we've gone back and we looked at our models. We're still doing a lot of work on micrometeoroids to go, gee, do we want to point in certain directions preferentially at certain times of the year? Because it's actually the background micrometeoroids that are a bigger threat. There's meteor showers all through the year. And you might think, oh, those are what we got to watch out for, the Orionids or Leonids. The Leonids are coming up soon, right? So should we point away from them so that the mirror's not going to get hit? So it turns out those are not that big a threat. The bigger threat is just the normal environment. And it's weird how they all come from certain preferential directions. So we're actually going to implement, starting in cycle 2, just to be safe, because abundance of caution, we're like, all right, let's when we're in certain parts of the orbit, certain times of the year, we're going to try to keep out of a certain cone of acceptance, and so that changes which observation you do during the year. Just because if you're in the RAM direction, my mirror's heading right into the breeze of the primary breeze of micrometeoroids. Let's try to avoid that when we can, and really all it does is reorder some of the observations that we're going to do in cycle 2 and beyond. It doesn't cut the science or screw up the efficiency. So yeah, so even though we got that well within expectations, we got plenty of margin, yada yada yada, we're still being really conservative and taking some proactive measures to make sure that we keep this thing as nice as we can for a long time. Sorry. God. This is what happens when you work on something for 25
Sorry.
No, I actually texted you that day because I was like, wait, what's this micrometer? It's going to ruin my art show. Okay, yes, we've got a question back here.
Hi, my name's Henry. I'm an artist and a big fan of space. I have a question for Elaine. So you mentioned clean rooms. I would like to know what exactly is that, and I think I understand the purpose of it is to keep the mirror clean. I guess my question to you is, what is the importance of it, and also how are the clean rooms maintained?
Okay, so let me pull up a picture of me. Okay, so clean rooms are used throughout the entire space industry. I would say basically every mission that we process at NASA is in a clean room of sorts. Now, depends how stringent and how strict the clean room is, depending on how sensitive your surfaces are, what are your goals of the mission. But I mentioned that we were in a class 10,000 clean room, and that means that within like 1 cubic foot of air that I measure, I can't have more than 10,000.5 micron particles. Now I have different restrictions for other sizes of particles, but the clean room classification is mostly based off of those 0.5 micron particles. And how do clean rooms work? So we actually have in this picture, you can see it a little bit, we have air inlets and then air returns. Ideally, you would want to have an air inlet up at the top and then returns closer to the bottom so that you could have airflow in the clean room that would go over your hardware. And then as it is dirty and needs to exit, it goes back out. And then it's actually processed through the HEPA modules, like I mentioned. So we have at Goddard, it's called the SysDiff clean room. It's actually the largest class 10,000 clean room in the world. And that's the room that we were in for Webb. So we have an entire wall of these HEPA modules that actually supply us with clean air and then clean up the dirty air out of the clean room to then recycle it back in. So I would say airflow is a big component of it. We are focused on the temperature and humidity. Usually there are strict requirements for the temperature and humidity depending on what materials you're using for your missions. And one of the biggest contributors of contamination are us. So people that need to go in and work on the hardware. So we actually require everyone to wear something even a bit more stringent than what I'm wearing here. We're usually covered from head to toe. So we have a head cover on, coveralls, boots, gloves, face mask, and they're called bunny suits. If you've seen anyone walking around in them, everyone that goes near the telescope is in one. So you need to be, really careful as you're up near the mirrors, doing any kind of work on it, that you're not generating particulate while you're doing those operations. So if you ever get a chance to see the clean room, you'll see, air inlets, air returns, where the HEPA filters are, and it's all just about trying to, keep the missions as clean as possible.
And people are the biggest source of contamination, right?
Yeah.
It's like Pigpen from the Peanuts cartoon. Seriously, so.
We use that in almost all of our clean room trainings, so we show that.
So, we wear these white burqas, basically.
Yeah.
It's really miserable being in the clean room for hours at a time, wearing those things, and I gotta go pee, so now I gotta leave the clean room, and then I gotta take all this stuff off, and then I gotta put it all back on. But but a huge part of everything we do, the stuff Elaine does, and this is an even bigger challenge. Now, clean rooms for like semiconductor wafer manufacture, those are even crazy. They're way crazier, cleaner than us, but like they don't even let people in some of those areas because we're such dirt bags. But the contamination team that Elaine's part of did just a bang up job on this mission. We were always like a factor 10 better on our clean room cleanliness. They measured the yin yang out of everything, making sure we knew where we were and how good it was, and they did an amazing job.
Yeah, and you did ask about monitoring. So I will mention that we actually have, this is just a handhold particle counter that I was using to qualify a new area, but we have particle counters that are running continuously, so we know the counts, we monitor temperature and humidity, and then I mentioned percent area coverage. So unfortunately, some of these sensitive surfaces we can't sample or measure directly, so we have surrogate samples. Now they're actually silicon wafers, and I can go and read them on a microscope, and I can tell you, how many particles there are, what size these particles are, and we make sure that these samples see the same conditions as the mirrors. If we clean the mirrors, we clean the samples. So we're usually using silicon wafers for the particles, the particle counters, and then we have some foils that we deploy, and then we rinse them to look at the molecular contamination, so that NVR that I mentioned. So clean rooms are monitored continuously to make sure that they're within the requirements set.
You can see it, it's a particle. If you can smell it, it's a molecular.
Yeah, there you go. That's all you need to know.
And then, you know, this launch site was a particular challenge because it's a really busy launch site. Europe uses it. A lot of commercial comm satellites that go to equatorial orbits and geosynchronous orbits that they say are the same spot of the Earth all the time are launched from this location because it's only 5 degrees above the equator, and they launch lots of ComSats from there. Well, ComSats don't have cleanliness requirements like something like us have, and we really expanded the envelope for these folks down there. So Elaine and her team, you know, spent years in advance measuring the clean rooms down there, figuring out that they weren't that great, what we had to do to mitigate it, and that included those movable HEPA filter panels that were like just big air. They were just blowing clean air on the telescope, and yeah, so it was an extra challenge working in this place. Really world-class facility. It was just they're not used to handling like giant exposed optics like us. We're like a really weird case for them.
Right. Yeah, it's really expensive and intensive to maintain this kind of cleanliness. So if you don't need to, you typically don't. So since they had communication satellites, we were the most stringent that they've had for their missions.
Oh, okay. Question?
So I'm a fashion designer and I do like a lot of quality control with my own garments. And there's 2 instances in this presentation where like you guys had mentioned something about testing. One time you had mentioned testing fabrications that were supposed to be in -60 Kelvin. And you're saying that you're predicting how they would react in different temperature circumstances.
Yes.
And then another instance you said something about testing the flow of air particles and that going on there in space where there's no wind. I was curious on how you guys went about that.
Yeah, so you want to take the first part first?
Okay, so the computational fluid dynamics that I was talking about is actually more so representative in the clean room, looking at the airflow. And I will say that we actually did look at this also within the fairing. It's really interesting to see how particles redistribute and what do those patterns look like actually during the launch environment too. Now, we're lucky that, as you mentioned, while we're in space, we shouldn't have any redistribution of particles. So we were mostly worried about that computational fluid dynamics for looking at the behavior in the clean rooms and then within the fairing.
Yeah, and then I guess your first part of your question was about 60 Kelvin and how yeah, so we built it at room temperature, but you know, the optics of the instruments work at, well, the optics work from anywhere from about 52 Kelvin down to 27 or so Kelvin, and the instruments all work at, the detectors and all those instruments work at 37. Oh, one of our instruments is super cold because it's these mid-infrared lights. So you couldn't get it cold enough just by passively cooling alone, so we had to put a refrigerator on the telescope to cool just that one instrument down to below 7 Kelvin. So how do we know that things are a certain way at room temperature, and we know very precisely what they'll be at some really colder temperature. And again, there's a lot of modeling anchored by measurements in that, and a lot of the actual testing. So when we put the whole telescope, for example, in that giant vacuum chamber, the relic of the Apollo era from down at Johnson Space Center, that's where we were actually lining up the optics and measuring them. And we can measure them with very high degree of precision with an interferometer and with other devices that we actually pass light through the whole telescope too. So and using the science instruments as cameras too. So that way we could measure very precisely what's going on. And we had models of what those things should be, and they ended up the test results ended up matching a model, or it's probably better to say it the other way around. But we didn't wait till that level of testing to do testing. Like every optic was tested as an individual optic and characterized through a range of temperatures before we started assembling everything, so we knew that we weren't putting bad stuff together that we'd have to take apart. But yeah, there's so much testing that goes into this as you build something like this up. And since you've only got one shot at it and it's one thing, it's just ends up being really thorough. But yeah, a lot of analysis coupled with a lot of measurements and a lot of correlating of that stuff together. That's basically how it goes.
All right, I think we have time for maybe one more question, and then we'll move the chairs back and do some people in VR. Thank you. Yeah, cool.
Thank you so much. This has been really amazing and inspirational. I was curious if you have an estimate of the lifespan of this telescope, and then if you can speak at all to the future. Like, what do you think is the next device and next question you're trying to answer?
Sure. So, so this seems kind of weird that you spend 25 years building it and only has a requirement to last 5. But the science mission that scientists laid out, they told us we want to get this all done in 5 years because maybe this thing won't last that long. So, but we designed it to last at least 10. And actually, where it is in space, it needs a little bit of propellant on board to keep it in its orbit and to manage momentum that gets built up from the fact that that big umbrella acts like a sail, and it catches solar pressure, solar wind from the sun, and that you have to dump that momentum. So you need something to push against, and that's what propellant is for. So we sized our propellant so that if we got a worst case launch from like a 3 signal, 1 in 1,000 crappy launches from Arion, we would still last at least 10 years. Well, we got a perfect launch from Arion, so we have enough propellant to last almost 30. It's been like the real number is between like 24 for oxidization, like 27, almost 28 for fuel. So good thing is we always thought fuel is the only consumable on the whole observatory that's guaranteed to limit our life, but because that's going to last so long, it's probably going to be something else that fails first, like some mechanism on some instrument or something, or something that's on the spacecraft that actually does the flying, the orienting, and the attitude control of the thing. One of those systems might die before we run out of propellant. So it's a really good problem to have. So hopefully this thing is going to last for way more than 5 years, even way more than 10. Sure hope so.
Yeah, and for what's next, there's a mission called Louvoir. I think that we are working on renaming it, but it has been as a response to the decadal surveys that I mentioned, trying to answer those next big questions. It's going to be a UV telescope, and we have our scientists and engineers that worked on Webb focusing on this effort to make sure that all of the lessons learned from Webb are applied to this telescope that is talking about having segmented mirrors. We'll need quite a large sun shield too. And I've seen efforts where they're trying to incorporate young engineers like myself into this because we hope to lead that project when it happens. So if you want to speak more on it, but
I'm one of the old guys that's mentoring Elaine and her generation. So one of the next things is, okay, Webb can do low resolution images of like large planets around nearby stars, like that one image I showed. But one thing that scientists are really interested in, the exoplanet scientists, are actually taking images of Earth-like planets around nearby stars, and that's a really, really hard problem. You need contrast ratios on the order of 10 billion. You need to suppress the light from the parent star by a factor of 10 billion or more, so that you can actually see the planet, the Earth-like planet that's orbiting near it, and then to actually have the size of your mirror and the sensitivity and the stability in the mirror to resolve that planet and like actually maybe make out clouds and stuff on that planet. That's kind of the next grail that a lot of scientists are reaching for. So it'll maybe look kind of like Webb, and like Elaine said, it'll have a big sun shield, be an open design, perhaps maybe a half a tube, because you don't want micrometeoroids to hit that thing. But the hard part of that isn't so much it's not going to be cold, it's going to be room temperature, because it's going to see mainly optical and UV and a little bit of IR. But the real tough nut to crack on that machine is stability. We're talking like tens of picometers or 10 picometer stability. So what's a picometer? Picometer is the distance it's basically the radius of an atom. So, okay, so I'm gonna build this thing that's got a 15-meter primary mirror, segmented, and then I'm gonna have to line it up to, you know, less than a nanometer. Oh, and it's gotta be stable to like 100th or 1,000th of a nanometer. That's just nuts. So, but people thought we were crazy 25 years ago when we said we were gonna build this big cryogenic space telescope, and they're like, yeah, you guys are smoking something. Well, but we're trying to, there are a lot of lessons learned from Webb that we can apply to that mission. It's just that I won't be alive by the time we launch it, probably. It'd be nice, but I don't know if I will be. So we're trying to pass our knowledge on by working together on this new telescope in its early stages, because you don't pass knowledge on by writing it down and just handing somebody a document that's working together that you pass that knowledge on effectively. So.
Will it take 25 years?
Right.
What's
She
25
said-
years?
She said, will it take 25 years?
Well, we hope not. We actually, one reason Webb took as long as it did was we went from basically concept stuff and knowing what technologies we had to develop to our preliminary design took 9 years. That's a long time. And then it took the last 14 to do the actual construction. And we probably could have shortened that by a couple of years if we hadn't had some just oh craps happen to us. But that 9-year period, that early period, if we can shorten that, because it's really hard to shorten the other end. It's kind of a finite process, you know, 1 woman, 9-month kind of process to build a telescope and test it. But this new one, because we don't have to do cryogenic testing, that'll help make it shorter. But that front end is what we got to shorten. And we think we know how to do that. But the biggest lever we have to shorten that is have a lot of money early. And of course, everybody wants money, right? But seriously, that's how Apollo worked. I mean, we had just launched our first human into space, and we didn't even orbit him. It was Alan Shepard, right, in 1961, and then not even a month later, Kennedy gives his famous speech at Rice University. We shall send a man to the moon and return him safely to the earth. I can't do the Boston accent, but era, and we will bring him home. And so that famous speech, and people were like, "Are you high? We're going to send people to the moon and bring them back alive?" And we just launched a guy on an overgrown Estes rocket. It was a suborbital flight. So, but the country spent almost 5% of its GDP in the 60s on the Apollo program in a short period of time. It was a crazy amount of money, and so we were able to build that infrastructure and make a lot of progress fast. And that's kind of the thing we're going to need for a new telescope, but it won't be anywhere close to 4.5 or 5% of GDP to build a telescope like that. It'll be much less, but that's going to be a key. If people are serious about building the next big thing after Webb, we can do it quicker. We can do it maybe 10 or 15 years, not 25, if there's enough money early to really get it going.
Right. Call your senators.
Yeah. And again, all the lessons that we learned, creating the segmented mirror, actually being able to align the telescope was such a big challenge that now we know how to do it. And the cryogenic technology is being used, a mission called Dragonfly. Is that going to Venus?
Titan.
Titan, yeah.
Moon of Saturn.
Yeah, Moon of Saturn.
It's a drone that's going to fly on
It's
Saturn.
so cool.
Titan, the Moon of Saturn.
Yeah, and they have to operate in cryogenic temperatures, and they've been working, with representatives from the Webb team to try and understand how we tested, what they need to know about working in these cryogenic conditions. So what's great is we're trying to spread the wealth of knowledge that we have learned on Webb and make sure that it's implemented for all of our future missions.
All right. Thank you so much to our two speakers. Don't worry, if you didn't get your question answered, we can hang out a little bit. We're going to clear the chairs out, put the sculptures back, and get people in VR. So stick around and hang out. Thanks, everyone.
Thank you so much. Thanks, Paul. It was so much fun to do this together. It really was. Thanks for pulling up a presentation, too. That worked well in the budget.
Yeah.
Thank you so much. Yes, of course.
Oh, let me check on that. Yeah, I'm trying to remember what actually.
Keep
Yeah.
talking into it.
Yeah, let me just check.
Well, we think we've seen objects.
Yeah,
back
that's
like
fine.
a sea of, like 300 of them. We think there's a galaxy that's